Okay, welcome back. So this goes under the heading of Chapter 14. And in Chapter 14, we're looking at intermolecular forces of attraction. And so we should probably make a distinction between intra and intermolecular. Again, these are just some general properties as you go through and read this. The big thing is that, especially for an application of this in biology, that you understand that intramolecular forces like ionic bonds and covalent bonds, those things act within the molecule to keep the molecule together, but an intermolecular force acts between the molecules. Now, generally speaking, ionic and covalent bonds, when we look at how much energy it takes to break them, you're looking at the range of about 500 to 1,000 kilojoules per mole of these bonds, whereas the strongest of the weak interactions at most would be about 50. So you're looking at about 5 to 50, not 550, 5 to 50 kilojoules per mole. So these attractive forces are really generally what we talk about when we're intermolecular, about whether or not something's going to be a solid, liquid, or a gas at a particular temperature or pressure, whereas intramolecular forces, you're looking at the nature of its polarity and whether it's ionic or covalent and more chemical reactivity. So again, properties of intramolecular versus intermolecular. And there are three different types of intermolecular forces. And the rule here on how strong they are: London dispersion is an intermolecular force that everything has. Doesn't matter if it's ionic, covalent, it has London dispersion forces. But they're very weak forces. They create what's called temporary dipoles. The electrons are moving at a very fast speed. And so if you have 20 electrons, let's say, in your atom, they're not going to be evenly spaced. Is it possible that at any given microsecond you might find 14 electrons on one side of the atom and only 6 electrons on the other half of the atom? And of course that's possible. The overall average is they're going to be fairly evenly spaced, but at any given moment they can be shifted to one hemisphere or another in the atom, creating a temporary pole where you have a deficiency of 6 electrons on one side and a surplus of charge where the 14 electrons are on the other side of the atom. But again, this is constantly shifting around and changing, so this is a very weak force, about 5 kilojoules per mole. Dipole is when you have a molecule that has a permanent polarity to it, and one polar molecule, the positive end of one polar molecule, will attract the negative end of another polar molecule, and this is a stronger interaction. These interactions tend to be about 10 to 20 kilojoules per mole. And then lastly, hydrogen bonding. Hydrogen bonding is not really a third category. It's a special dipole-dipole interaction where the polarity of the material is created because hydrogen is bonding in the molecule to either fluorine, nitrogen, or oxygen, and it's creating such a large polarity, a large dipole moment, that it's almost a full coulombic charge, and that makes it a very, very strong dipole-dipole force. And hydrogen bonding generally has a bond dissociation value of around 50 kilojoules per mole. All right, so again, London dispersion. Neon has 10 electrons, but are they all going to be evenly spread out at every given microsecond? And the answer is no. We could have this, for instance, this particular neon atom has its 10 electrons shifted towards the left hemisphere, creating a temporary negative side and a temporary positive side, and that positive side will attract the electrons of the other neon atom and creates a very temporary, very weak interaction between the two, what we call London dispersion. And it's not named after the city, it's named after a scientist whose last name was London. Again, dipole-dipole, you have permanent polar molecules. So the negative of this molecule, better use a different color. I don't know, purple. Negative of this molecule attracts the positive of the molecule below it. It attracts the positive of the molecule to the right of it. If I was to draw another molecule up here, it would attract the positive of that molecule. So you're getting a much stronger interaction between the molecules. And then finally, hydrogen bonding. This hydrogen-oxygen, this bond, is so polar that we have almost a full positive where the hydrogens are and a full negative where the oxygens are, and it creates a very strong attraction between the positive hydrogens of the first molecule and the negative oxygen of the second molecule. Hydrogen bonding is important, especially in biology. It is hydrogen bonding that creates the alpha helix in DNA. That interaction between components of the DNA strands causes this shape, this twisting shape, which enables DNA to be replicated. And then lastly, here's a summary again of intermolecular versus intramolecular forces. And the truth of the matter is, this is all we're doing in chapter 14. Focusing on intermolecular and intramolecular forces. All right, so what is the test going to look like? Glad you asked. Let's go back and make you feel comfortable. Okay, so the test is going to be multiple choice, and there are some practice tests in there. I used to combine chapters 12 and 13 together. That made one really big, huge test. I since have separated the two. So you're looking at chapter 12, and you're really only looking at 14.1, I think it is, for those intermolecular forces, and that's all multiple choice. I posted a study guide for it, and I'm going to say some brief things about it. I'll make a video tomorrow and post it tomorrow evening. But really, all you have to do is a little bit of study. I'll give you the instructions on how to go online and take the multiple choice test, and you should do well. So I'm hoping to do a Zoom.com type of meeting where maybe I can hear your voices and we can try to get as many of us together when things get more complicated in chapter 13, especially when we talk about hybridization and stuff. But for now, I hope that, at least this broke up the monotony. I'm not going to apologize for giving you work that was substitute-ish type of work. I just wanted to keep you moving forward. And as I figure this stuff out, I think that the materials will get better. And I ask you to just bear in mind because, I don't create online content. The people I showed you, Bozeman and Khan Academy, those people already have that content. So I'm hesitant to make my own content, but I thought, between my voice and this guy's face, that you might feel a little bit more comfortable with things. So thanks for your time, and hope to be in contact with you soon.